Hello, physics students. This is Dr. Brenzy here. So, this is a continuation of lesson 2.1.3, and we're going to be talking about using force diagrams to figure out force, mass, and acceleration. Okay, so in class today we did a master check here, and this is the same master check, where we have a helicopter holding a 70 kilogram package suspended from a 5-meter long rope, and it accelerates at a rate of 5.2 meters per second squared upward. And this says neglect air resistance, so we don't have to think about air drag. So part A says draw a free body diagram of the package, and part B says determine the tension force on the rope. Let's do part A first. So let's draw a free body diagram. So over here we have our package. And let's see, the forces we have acting on it. We have gravity acting on it. The force due to gravity. We have the tension in the rope acting in an upward direction. Okay, so those are the two forces acting on our package here, our 70 kilogram package. So what I want to do next is make sure that I define a coordinate system. So that was the second step. So let's say that positive is up and negative is down. And then I'm going to write out Newton's second law, which states that the net force on this object equals mass times its acceleration. Now I'm going to plug in what was given. So let's first of all make a list of what was given. We know that the mass is equal to 70 kilograms. And we know that the acceleration that our package is experiencing is 5.2 meters per second squared. All right, so let's plug in what we know into our second law, and we get our net force is our tension force plus our gravitational force. And I do realize in my last video that I put a minus sign here, but from now on I want us to think of this always as plus, and then when we plug in numbers, then we'll start thinking of sign, whether it's plus or minus. So that equals the mass times the acceleration. All right. What is my mass? It's 70 kilograms. What is my acceleration? It is 5.2 meters per second squared. And it says acceleration is in the upward direction. So the sign of that needs to be positive. So that is what I'm going to have on the right-hand side of my equation. On the left-hand side, I have my tension force, which I don't know. I'm being asked to find that out. And then I add to that the force due to gravity. Well, the force due to gravity is always equal to the mass times the acceleration due to gravity, g. Okay, and since it's going in, g is going in a negative direction, we're going to write this as mass, which is 70, times negative 9.8, because that acceleration is in the down direction. So this force of gravity is equal to 70 times negative 9.8, so I'm going to plug that in here, 70 times negative 9.8. All right, so now I just need to simplify and get the tension force by itself because that's what I'm being asked for in the problem. So tension force plus, let's see, this is going to be, I believe, negative, let me find my calculator. It's going to be somewhere around negative 700, I know that. But if I want to be more exact, 70 times negative 9.8 gives me negative 686. All right, so negative 686 equals 70 times 5.2. And that gives us 364. All right, well, I want tension force by itself, so I had better add 686 to both sides. Okay, and you might be asking yourself, why, Dr. Brinzy, why are you adding when there's a plus sign right here? Well, we are adding a negative number, which is the same as subtracting the positive, and the opposite of subtraction is addition. Or you can think of it as, if I want to get this back to 0, what do I need to add? I need to add positive 686. Either way you think of it, we need to use addition. So our tension force equals the sum of these two numbers, which turns out to be 10,000, or 1,040, excuse me, 1,040 newtons. So if you got that for your mastery check, good for you. If you didn't, there'll be another opportunity to practice problems like this tomorrow. All right, now I also want to talk about some of the problems in the practice that we did today, because there might be some vocabulary that's a little bit confusing to us. I had a lot of questions today about vocab, about certain things here. So I'm just going to go through a couple of these that I noticed we had a lot of problems with. All right, so let's go through this number one right up here. That number one says a 6 kilogram block is at rest on a table. A 12 Newton upward force is applied to the block. What is 10 times the force the table exerts on the block? So let's go and go to a blank whiteboard here. Let's actually draw that scenario here. So we had a box on a table. All right, and if I remember right, the mass of the box is 6 kilograms. And it was saying that somebody is exerting a 12 Newton force on that box. Okay, those are the things that I'm given. What am I being asked for? It says it was asking for what is 10 times the amount of force that the table exerts on the box. Wait a minute, the table exerts a force on the box? Well, that's another way of saying that this surface exerts a force on this box. Well, when we have a box lying on a surface, there's a force acting on this box. What do we call it? We call it the normal force. So basically, it's asking us for the normal force, F sub n. We don't know what that is. But we're going to find out. So let's draw our free body diagram, because that's the first thing we do when we solve Newton's second law with forces in different directions. So let's draw our free body diagram. So in the upward direction, I have two forces acting. I have this normal force, and then I have plus another 12 newtons in the upward direction. Okay, what is acting down on the box is the force of gravity. And since I know the mass of the box, I can already calculate the force due to gravity. That is m times g. And we know that m is 6 kilograms. and G is negative 9.8. We'll keep that there for now. And when we need to use it, we'll bring it back up again. All right, so after I do that, I need to define my coordinate system. So let's make this the positive direction. Let's make that the negative direction. Seems pretty straightforward. All right, so after that, I need to write down Newton's second law, F net, I almost forgot the net part, F net equals mass times acceleration. All right, so F net is the sum of all my forces, so I have the normal force plus 12 plus the force due to gravity, okay? And all of that equals mass times acceleration. All right. Well, let's start plugging in what we know. Do we know the normal force? No, we don't. As a matter of fact, that's what we're being asked to figure out. That's the force that the table exerts on the box. So let's leave that as F sub n plus 12. And then we have plus 6 times negative 9.8. All of that equals our mass, which is 6 kilograms, times our acceleration. Now, I wasn't given a number for acceleration in this problem, but I'm wondering if I can figure out what it is. Well, it told me that this box is at rest, right? So if this box is at rest, what is its acceleration? Is it changing velocity? No, it's not. It's staying at rest. So if it's not changing velocity, what does acceleration have to be? It has to be 0. So let's put 0 right here. All right, and now we're going to start simplifying and evaluating here. So F sub n and plus 12, and then I have to take 6 times negative 9.8, and I get 58.8, or negative 58.8, so let's write minus 58.8. That's not the greatest looking 8 in the world, equals 6 times 0, that's 0. All right, so F sub n minus 46.8, not 4.68, 46.8 equals 0. All right, should be pretty straightforward how to solve this. Add 46.8 to both sides. You might not have needed to see that, but our normal force, F sub n, equals 46.8 newtons. Okay, now, except there are a couple things here. I have to care about significant figures. All right. Now, I just wrote 6 kilograms here, but I know that in the problem, it actually wrote 6.0. Okay, so actually it was 6.0 kilograms. So that has how many significant figures? That has 2 significant figures, right? The other number I was given was this 12 newtons right here. How many significant figures does it have? That also has 2 significant figures. So my answer in newtons should be expressed with only 2 significant figures. So instead of 46.8, the answer that I'm actually going to report is 47 newtons. All right, and that's actually my final answer. All right, well, actually I just realized I left out one last thing. It actually asked us for 10 times this force, right? So actually, the answer to the question that it actually gave to us is that it would be 470 newtons. Now, you might be saying, Dr. Berenzi, why in the world did you ask us for 10 times the amount of force? Well, it's because of the little activity that we were going to do along with this, but we ended up just working on the problems themselves. So we really didn't get an opportunity to use this number the way that I had intended for the activity. So usually you're just going to be asked for the normal force. All right, so this was just for our activity today, so you can kind of ignore that whole 10 times thing. You normally won't be asked that in a physics problem. All right, before I let you go, just want to talk about some vocab for some other problems because we're going to turn our attention back to them tomorrow. So let's go ahead and let that go. All right. One thing here, problem number 3, this problem right here about the tree surgeon. Now somebody asked me, Dr. Bernsey, what in the world is a tree surgeon? Well, somebody goes around and trims trees. Like if they get too close to electric wires, somebody has to go in there and trim the branches back. That person's called a tree surgeon. Why did they call it surgeon? Yeah, it beats me, but they call them tree surgeons. There's a thing called a cherry picker. Now, you might not be familiar with that term if you are not in like construction or any sort of field like that, or if you don't have a parent who's involved in construction. But a cherry picker is one of those things that they use to lift people up. So maybe you've seen like the electric company or the telephone company, and if they're doing like work on some wires way up here on a telephone pole, what they're going to do is they're going to pull up their truck in a truck, right? And in the back of that truck is going to be something called a cherry picker. So it's like an arm that comes out, and then at the very end of that arm is a little bucket, and then our little guy stands in the bucket, and he's actually raised up in this bucket so that he can repair the telephone wire. So this thing right here is called a cherry picker. All right, so if you're having a hard time visualizing what's going on with this whole cherry picker thing, that is exactly what it is. So this problem is talking about this cherry picker lifting this guy up, moving up at a constant speed, and then even accelerating down at a particular acceleration. All right, so I think that's all I'm going to cover for today. I'm already running on 18 minutes, so we'll work on this again in class, and we're definitely going to make sure that we have these problems down. Yes, they are tough problems, but this is also good for helping you do problem solving in life in general, because some problems can be tough, and you got to have the grit to persevere through them. So we're going to keep working on these tomorrow. All right, class. Hope you have a good evening, and I'll see you tomorrow. Bye.